it gives me immense pleasure to introduce Dr. Nirav Lekinwala, who I can proudly say is one of our alumni. So Nirav did his PhD at IIT Bombay, working with two guides who are close collaborators to me. Dr. Nirav Lekinwala is a senior associate in the air quality modeling team at the Center for Study of Science, Technology and Policy. It's called C-STEP, which is a not-for-profit. Am I correct? Yeah. So at C-STEP, he works, so it's a think tank. At C-STEP, he works closely with Dr. Piyush Bharadwaj on implementing advanced air quality models such as WRF-CAMX. His work primarily focuses on supporting data-driven, scientifically grounded policy recommendations to support air quality management in India. We all know how serious the air pollution problem is in this country. Dr. Lekinwala completed his PhD from IIT Bombay. During his doctoral studies, he gained significant expertise using numerical models and statistical techniques to understand various pollution sources. At C-STEP, he applies his multidisciplinary background to develop actionable insights for policymakers, contributing to sustainable and effective air quality interventions. His interests include atmospheric data analysis, air quality modeling and evaluation, and enhancing the integration of scientific research with public policy. Is there anyone here who's from a public policy background or social sciences background? One. All right. Over to you, Nirav. I'm looking forward to it.
Thank you. Yeah. So I think, is this mic on? Yeah, turned it on. Okay. So first of all, I'd like to thank Professor Arpita for the introduction and Dr. Mitra for inviting Piyush and then me to this workshop. So today I'm going to talk about using machine learning and low-cost sensors to validate air quality models in India. Does anyone of you all have an idea about what air quality models? You've been hearing about a lot of the general circulation models and all. Does anyone of you know what an air quality model is? Okay, so let's start. Before I jump into what air quality model is and what we do at C-STEP, and then how do we translate those to policies, I'd like to give a brief introduction and tell you what C-STEP is. So C-STEP is a think tank. It's a Bengaluru-based think tank, and the mission is to essentially enrich policymaking with innovative approaches using science and technology. We have multiple groups, verticals in C-STEP. We call them sectors. Air quality is one of them. We have climate, environment, and sustainability. We have energy and power, renewables, strategic studies, and AI digital platforms. As Professor Arpita said, we are a non-profit think tank, and we're mostly supported by grants from governments, industry, trusts, domestic and international foundations. And I am part of the air quality modeling team, which is part of the air quality sector at C-STEP. So what does air quality sector does? We work towards finding solutions to several grand challenges of India. Internally at C-STEP, we have several grand challenges that we try to solve. Clean air for all is one of them. The sector is led by Dr. Subramanian. And at C-STEP, we work with different national and state governments to assess implications of existing policies, suggest policy recommendations to improve the overall air quality for the state. And as part of the National Clean Air Program, which is one of the programs started by Government of India in 2019, which targets to reduce the PM10 concentrations across India, we are Institute of Repute for the 4 non-attainment cities in Karnataka. So essentially, we provide technical assistance to these cities. We do capacity building workshop, go talk to them, try to understand what their understanding of air pollution is, and then try to kind of help them technically to kind of improve their air quality. And in the air quality sector, we use the chemical transport models such as WRF-Chem and WRF-CAMX. Currently, we're using WRF-CAMX for its use in air quality management. And we also work with several academic partners, be it in India or outside, to develop several reduced complexity models which the policymakers can use. These are some of the outputs that we have normally. Like, we do publish papers, but most of our output is in form of either a policy brief or a report, which is easily accessible and is less technical as we write a research paper, but more so that people can easily understand it. So as part of one of these research brief on black carbon, where we looked at how much of black carbon is affecting changes in temperature, changes in rainfall, and others. So these are some of the outputs that we have, and many more. And in the air quality modeling team led by Piyush Bharadwaj, we run state of the science chemical transport models such as WAF-Chemex. We also are working towards developing reduced complexity models. So not everyone has the luxury of having a high performance computer at their home or at their institute. So for such people, we develop reduced complexity models which you can run on your laptop. Uh, and you can get like annual exposure of PM 2.5 to, let's say, some population over India. Um, while, like as I said, people don't have the luxury, we do have some luxury in that way. We do have some in-house computing capacity, and all the things that we do is mostly open source. We develop a lot of in-house codes that for machine processing and results and data visualization. So this is an overview of what we do at CSTEP, just to give a background uh, of what CSTEP as an institution do. So this is going to be a brief outline of what I'm going to do. I'm going to discuss what the modeling setup at CSTEP is, and then why model validation is important. What is model validation? Why is it important? And then I'm going to then delve into the main topic where we are going to use machine learning, which is low-cost sensors. I'll briefly talk about some of the calibration methods there, discuss the merits and demerits of some of these methods, and then a case study on how we can case study for Bengaluru, how what we have done in the last 1 year at CSTEP is kind of we can use it for modeling. So this is our basic setup. We use a WAF model. We rendered multiple resolutions. So one of the recent modeling setup is that we run a 27-kilometer India level grid, and then we go down to a 9-kilometer grid for a smaller region. State level we go down to 3 kilometers, and if you want to go down to city level, we do it at 1 kilometer. So this is our WAF setup. We normally have we take the global reanalysis data that we get from ERA5 at different pressure levels and surface that goes into the WAF model, which then generates gridded meteorological data at hourly resolution. Once along with this, we then use emissions data. So you have the meteorological fields, the temperature, pressure, your temperature at different levels, pressure, and then we have other rainfall and other things. Along with that, then we have emissions data. So for any air quality model, you need to emit something that is been naturally done. But for a model to understand where and how much is it emitted, we use emissions inventory. Sadly, there are very few emissions inventory based out of India. So we have to, currently we're depending on global emissions inventory, which are currently at like 10-kilometer resolutions. Over a pixel, it will tell you from what sectors and how much of a particular pollutant is being emitted. It also needs, so we also use some ozone data, the photolysis data, and other global model outputs. So there is, we have a model called ChemChem, which because we are running it over a certain domain, and I'll show you the domain, over a certain domain, what comes outside the domain needs also to be captured. So that is where the global model data, where it's run over the whole world, comes into picture. That helps us generate the boundary conditions, the initial conditions, the boundary conditions for the ChemX model that we run. Now all of this is then interconnected. You take the meteorological data from WRF along with some ocean related data, the emissions data that we have that from different global inventory. I'll talk about it in the next slide. Then we have some of the other utilities. These are all the utilities that you get with ChemX, and then basically generate inputs for the ChemX model. And okay, it's not working. Sorry. This is like the output of the output that you will get from ChemX. So you will see this is like my whole domain. This is India this simulation is at 25 kilometers. And you see that this is basically the PM 2.5 concentration. And the scale is up to 120, and you can see that, over a large region, and let's say Balochistan, which is like a desert area, and even the places over Rajasthan, you see very high concentrations. So now currently we're at November, and you see, even though the South India is relatively cleaner, you have a backflow from the Indo-Gangetic plain that comes, and then that's when you see high concentration during certain months. So this is like the output that we can get. Now, what do we do with this Before we can use this output, let me just talk about emission inventory and then I'll talk about model validation. So emissions inventory is one of the important inputs to the model. You can, you can go wrong. Your model will give like very wrong results if your emissions are not correct. It essentially captures, so this is our hybrid inventory. It essentially captures what are the different pollutants from different sectors that are sectors as in just different sources of pollutions that are emitted. So we have, for example, we have waste burning, energy like power plants and others. We have agriculture. Agriculture on itself will generate a lot of methane and ammonia and other things. But then there is also agricultural waste burning that comes, which is one of the problems in India. We have forest fires in India. Not a lot of people know, but we do have a lot of forest fires in the northeast and near the Himalayas. We have the biogenic emission, the natural dust. Ocean also emits a lot of it. We have aviation. So all of this then comes together to form our hybrid emission inventory that we use in ChemX. And we use different sources. And the hybrid approach here is essentially to take different sectors or sources that we call from different global emission inventories. Based on how they're spatially, based on the spatial variability, there are some emission inventory where the transport sector is very, they are not represented very well spatially. So all those things we take into account, and then basically we create a emission inventory. So this basically tells us and of course, a lot of this is also done in literature. So this basically forms our backbone, like the emission inventory, we call it hybrid emission inventory from different sources. So this is how the emissions would look. Like this is, again, I've cut out a lot of other parts, but the original file has it. This is the emissions. This is in terms of tons per grid, per 25 square kilometer, how much tons of a particular pollutant is emitted. Here we have PM 2.5 in the spatial map, and these are some bar for different, for a lot of other pollutants. And you see that, over cities, you'll see large red dots because, a lot of emissions you get from transport sectors and other sectors that are there, very localized to a city. We also see other areas, like for example, here you see point sources. They are essentially from large power plants. All those then, it basically emits, and then when you run the model, it mixes throughout and disperses these pollutants. You also see a yellow band over the Indo-Gangetic plain, which shows that there's a large amount of, it's not point, so basically not like a city or for that matter a power plant, but then because of the prevalence of using wood biomass for cooking, you can see that the domestic sector here, if you see in PM 2.5, it is one of the largest domestic sector. So it is also contributing a lot to the pollution over India. So as I mentioned here, dust is large for PM 2.5 and 10, especially in PM 10. Transport is major contributor of NOx. So here, if you see NOx, the transport sector is the largest. We have large contributors from contribution from industry and energy for SOx, NOx, OC, and black carbon. And we have domestic large contributes largely to PM 2.5. So this is what goes into our model, and this is the output. So basically, what results we get is essentially spatio-temporal concentration of PM 2.5 and other species over the domain. The animation that you see is daily averages, but ChemX has the ability to give you hourly concentrations of PM 2.5 for a particular grid. And then there are also certain tools. So here I'll talk about it. There are also certain tools such as PSAT. For example, what if I'm a policymaker and I'm a policymaker sitting in Karnataka and I want to know what is the contribution of neighboring districts, domestic sector to, let's say, Bengaluru's pollution, or for that matter, other states to Bengaluru. So all those studies you can do with ChemX. You can tag a certain species, trace a species, and it basically will tell you if you turn off emissions everywhere else but that region, how much will it contribute to, let's say, Bengaluru's air pollution. So all those things you can do with ChemX. Such insights are useful in policy making, and model can help us test various interventions. Now, let's say Karnataka government is planning to, let's say, phase out all the buses in Bengaluru. All the fossil fuel buses, they want to move to electric. How will it affect? Before even implementing, you can do certain experiments with such models, and it will tell you how much improvements you will get in the air quality. So this is a lot of this can be possible with models like ChemX. So this is just an overlay of how the emissions are. If you see at a lot of these places, for example, here, you see that there's a power plant, and when it emits, it shows black region around it. So that's how it's dispersed. Okay, so but can we trust these results? So like models can give you whatever results you want. It needs to be validated. So that is when model validation is the key. And the whole my talk, this was just an introduction. Was building upon for this point that model validation is one of the very important things for anyone. If I tell you that this is the source of pollution to Bengaluru, I need to back it with some evidence. This is how it helps. If your model is working well, then you can say that my the result that the model is validated well with observations, and I can say that my output that or the results that I'm giving are correct. Okay, so model validation, because we are using two models. WRF is the first model that we run to generate the meteorology, and then everything else. It's a one-time job. Once you have the WRF run ready for, let's say, India and at a different scales, you just have to rerun ChemX. So that it's a one-time thing, but we still validate these models with some from the observations data that we have, like Mitra and Synop. We also have a lot of the CPCB. Has anyone heard of CPCB's air pollution network? Like they have a CAQMS network, which basically tell you AQI. For normal people, they'll tell AQI that it's severe. You may have heard of Delhi banning cars for certain days, odd even. All those are based on AQI. So how do they get those values? They get it through a network, and you see that there's a dense network of this continuous air quality monitoring stations near Delhi. But then there are some areas where there are hardly any. So unlike meteorology, we get speciated concentration from these stations. And for some reason, as of yesterday, I don't know about today, a lot of the stations in Haryana were not working. I don't know why. So this again is an issue. You might not sometimes have reliable data, or they may be under maintenance. You may lose data for some days. So this is the network that we have over India. There are 463 operational as of yesterday. So we use this data to essentially validate the ChemX model. Once the WRF model is validated using the other observations that we have. However, okay, so now I'll show some of the results that we have. So this is the CPCB data. On the x-axis we have observations, and this is something that we get from ChemX. So you see that they are well in the range of. So again, this is a 1-on-1 line. We have a 1:2 line, 2:1 line, and we see that they are in that range. Most of the points are in the range. But then some might say, oh, you said 463 points. Why do I have very less points? The problem here is that for a city like Delhi, where we have 40-45 stations, model can only have like 3 or 4 pixels over that region. Okay, and if you want concentration as all those points, it is going to give you same result, because the model all of the pixels lies in the same, all the points lie in the same pixel. So unique points in the models are very less, where let's say for example for Bangalore also, I'll show one of the plots I think I have somewhere, that there are I think 13-14 stations, but only few of them are usable, like in the sense that a lot of them fall in the same pixel. So you see that the comparison here is good. So the quality of the problem here is the quality of the CAQM register also a problem. You will have a lot of missing data. Like I said, I showed the plot where Haryana is missing, and it will say missing for some days. You never know when it will come up. There are same values over days, and then there has been some cases where you will see that over 10 days the values are exactly same, which either is malfunctioning or some other issues. There is also drift in the values for essentially for electrochemical sensor, like the gases which are measured using electrochemical sensors, they will drift over time. You need to recalibrate it like frequently to kind of get reliable results. Additionally, all of this network is city focused. You saw that you see here that there are so many stations around Delhi, some around Mumbai, some around Bengaluru, Hyderabad, but then rest we don't have a lot of it. So that also is an issue. So this is that Bengaluru map that I was talking about. We are covering Bengaluru in around 28 pixels, the whole of Bengaluru, and we get, I think, only 12 usable locations. So, for example, for F, there are three sites in the same pixel. It is going to give the same result from the model. So this is where if I want to go at a smaller scale, the things might improve, but still, if I want to go at a 1 kilometer scale for city level modeling, it's still difficult. You will not be able to validate a model well. So if we have low cost sensor network, and I'll talk about what low cost sensors are, and we augment that data along with the CPCB CQMS, it will help us improve our model validation. Improved and a better model validation, or a model which is which we are confident, which we have validated against observations, we can then very confidently talk to policymakers about the results that we have got. So that is how this model works. What are low cost sensors? So low cost sensors are very small portable devices. So this device will be like this big, and it'll basically measure PM 2.5, PM 10, SOx, NOx, ozone, and a couple of other pollutants. So that it is low cost. I mean, low cost as in it still costs 3-4 lakhs, but it is way less than the 4-5 crores that you have to spend on setting up a CQMS network, and you have to spend a lot on its maintenance. So in basically, let's say a 4 crore budget that you have, you can buy 100 or 200 such networks and place it across the city. But the problem with the local sensors is currently CPCB does not consider them as does not consider their use them for to be used for regulatory purposes. So I cannot report AQI for my region using the LCS data because it is not allowed by the CPCB. So you can use it for your research work, whatever you want to do, but not for regulatory purpose. So some state government cannot decide on a particular industry's fate, whether it is polluting or not, using a low cost sensor. It needs proper regulatory monitors to be used. However, it is it started to gain tractions. For example, this is one of the recent news in 2025 where BMC has mandated air pollution sensors at construction sites. So these are IoT devices. The municipal corporation will know what are the concentration at these sites where the construction is taking place, and then they can take decisions based on if it's a dust storm or something, you see a lot of concentration of PM 2.5, PM 10, they can ask them to hold the construction for a certain time. So all these things are coming up, but again, it's slow in implementation and so on. So why do we need to calibrate these sensors? Low-cost sensors are essentially, in India especially, they are off-the-shelf. They're basically assemblers who will take off-the-shelf sensors and they'll just put it all together. They will calibrate it on their own. Some of them do, some of them don't. But the idea is that we don't know what that calibration is. Manufacturers are often not very transparent about what their calibrations are. So the idea is that we get these sensors and we calibrate on our own. So for gases, essentially, it uses electrochemical sensors which converts chemical concentration into electrical signals, and that basically we use some equation to get the concentration back. And here, manufacturer has some calibration, but we ideally would want a user-defined calibration, which then we can tweak around. Same for PM sensors. It is an optical particle counter. You have particulate matter. It goes through light scattering based counter, and it basically places into different bins based on their sizes, and that's how you get different concentrations of PM 2. PM 1, 10, 2.5, and so on. Okay. So this is the methodology that we have been using for calibration, and at CSTEP we have a facility called INDICET, India Sensor Evaluation and Training Center, where we have reference grade monitors, and a lot of manufacturers send their sensors to CSTEP. We co-locate them, and then the data that we get from sensors and the one that we get from the reference grade monitor, we basically evaluate how close they are and can they be improved using a machine learning to basically improve their performance. So it is basically, we have an air quality monitoring station which is reference grade 1, and we have sensors from different manufacturers. You collect data, a lot of the data including PM 2.5, 10, some gases. We have atmospheric temperature and relative humidity. Again, we do a lot of cleaning. Time needs to be synced because a lot of this sensor manufacturer would report time in UTC, you have it in India, you are in India, so all those corrections needs to be done. And we also have some species-wide dependent functions, which essentially will tell me, for example, PM 2.5 is directly proportional to relative humidity. So you have, relative humidity, you have more relative humidity, the concentration is going to increase and so on. And this essentially then goes into your test trains. We split it 80-20 to basically then check how we're building models. And we have multiple methods. I'm going to talk about linear regression, quadratic regression, random forest, and XGBoost today. We then, if we have multiple sensors, you can either build a sensor-wise model, or you can build a manufacturer-specific, generalized model for 10 sensors, let's say, if they have. So this is how we essentially, this is basically the methodology. The data that we get for each of the model, we use multiple metrics to essentially rank them, and then we select a model for a particular sensor or a particular manufacturer. This is like the facility that we have. Just next to it is reference grade monitors. We place them on the test bed like this, and all of them, then basically data is collected, and then we kind of calibrate it. So the objective here is to create a calibration model and to estimate, which can be used to estimate the pollutant concentration on an on-field sensor. You can place it at the INDISET facility, but then if you're not going to place it in the field, it's of no use. So for initial 2-3 months, we do place it in the INDISET. We create the calibration model, and then they're deployed, and then we see how they're performing over time. So I'm going to talk about 4 of these methods. We have linear regression and quadratic. We have parametric methods, and we have random forest and XGBoost, which are non-parametric methods. So we'll start with a very basic linear regression. I mean, all of you would have kind of or learned it somewhere. It essentially helps me build a linear relationship between the independent variable and the observed variable. This is a basic solution. If you kind of derive it, you're going to get this this expression to calculate it for any x. And this is a multilinear regression. So here, while I'm showing y is equals to beta 0 plus beta 1 x1, it can be n number of such variables which you can use to build the model. And this is like a very basic code. I have included it. If someone has some questions, you can ask. So essentially, we have X. I'll take a data for one of the sensors, and I'm going to take certain variables that I know are going to affect basically the concentration of that particular pollutant. And because we have the reference data available at 15 minutes, we're going to resample it at 15 minutes. And I'm going to make sure that the time for both of these sensor and AQMS are synced together. Then we perform a test train split, and I'm just fitting a basic linear regression for it. And because I want an intercept, I'm also adding basically a row of ones, a column of ones. And then we're just going to compare the results basically for the training data and the test data. So here is what one of the for the linear regression we see. This is the data of ozone concentration. So this starts from 25th of January, and we have it till I think 24th of February, about a month-long data. And you see that the sensor data is off. Okay, and when you see a scatter plot here, you see that at lower concentrations the values are fine, but as the concentration of as the concentration increases, the sensor reports a very high value. So this is something we need to correct, and a basic linear regression fit will also will do the job. So the green line here, I'm not sure how visible it is, but the green line here shows that most of the points which were here have come down near the one-on-one line. So you see that for linear regression, we see an R square of 0.83, and I'll keep this bar here. I'll keep adding numbers here so that we can compare how it has performed. And again, this is not the only metric that we use. We have a lot of other metrics that we use, but for this presentation, I'm just sticking to R square for our work. The second method is going to be my quadratic regression. So quadratic regression is similar to linear regression. You don't have to change a lot in the code per se, but then you will also consider, along with let's say all the variables, you'll also consider the squared terms. Okay, you'll also consider the cross terms in it. So basically, it's an extension of linear regression, and as the number of variables. So let's say for 2 terms, we can have square, the cross term, and the square of A, B, and B. But then as you increase the number of points, the number of total possible combinations and the cross terms increases drastically. So again, here you have to choose between you want a very complex model or you stick to the basics using linear regression. However, we do some kind of selection based on how significant a particular variable or a particular term is contributing to the overall output, and that's where we use p-value selection. We only select those combinations which has like significant contribution to the overall results. This approach helps us kind of reduce the number of variables and simplify the model to and also enhance computational efficiency. So same thing, we have the same x and y's. However, before doing the test train split, I essentially use a polynomial feature. This code essentially helps me create all the possible combinations for the variables that I have, which are 4 here. And for this case, I am using all the variables, but then there's an additional part where you can select only particular variables or the combination of variables which are significant. So again, test train split, I'm still using the linear regression because it's similar to it. So this is again, where the plot go? I think the plot went somewhere. There's a plot here. I don't know where it went, but we get a good R square value for quadratic regression of around 0.9. So this again, you see that there is a slight improvement by including the square terms, the cross terms into the total equation, overall equation. The third method here is random forest. So random forest is an ensemble learning method where you basically use the data and you let it draw different decision trees. And this decision tree is built on bootstrap data. So basically you give them 100 points and it will internally mix and match. It will shuffle the data to build a large number of trees. And the final output of the final prediction is basically average of prediction of all the trees. And internally, this also helps us, basically remove any biases. So basically, if there are 2 consecutive values, because of the randomness, that null is captured, fixed here. We don't have any correlation between 2 points which are next to each other. Also, the averaging process also reduces the variances and fitting over bias. For example, a particular tree may be, not working well, but then others will kind of catch up, and the averaging process helps. And internally, it also has this concept of, so this is similar to cross-validation. So internally, it has something called an out-of-bag error. So if you provide it 100 values to train on, it will internally select only, let's say, 80 to train on, keep 20 aside, and then internally it will basically check. So we don't have to provide it a special validation data set. So this is a code a little more complex than linear regression, and here there is a concept of grid search. I mean, this is very technical in that way, but then we have a lot of parameters to such methods. For example, number of estimators, the maximum depth of the tree, the number of leaves at the nodes. So this basically helps us basically search through all the possible combinations of the parameter space, and then it will basically give you the best model. So that best model is what we use. So the best estimator is what we use to basically predict our output. And this is how it essentially does it. And before showing the graph, I'm just going to give this example. So for example, this tree is built for PM 2.5 and RH. If you have a PM 2.5 value of 100 and let's say RH is 80, so at the first condition here is that the PM is less than 94.98. So this condition is false. So if it were true, you would have gone here. But if it is false, you're going here. Here it says RH is less than 55, which is not the case. We have RH more than 80. So again, we'll go here, false. Again, it says RH less than 59.97, which is again false. We come here. So this is the value. So for my PM 2.5 value of 100 and RH is 80, my tree is predicting a value of 103. This you can do, I mean, internally does it for a lot of trees. So this is just one example. So this is what, I was going this, the hit animations. And this is like the output. you see that for R square, again, we have for random forest, we have again an R square of 0.9, which is quite good as good improvement over linear regression. However, there is an issue. You see that a lot of this values are same. For the observations, that multiple observations value we have, the tree is predicting exactly same value, and that may be because of this reason. So it will, for example, if I give it 110, all these conditions will still be true and it will give me 102. Anything more than, even if I have a PM concentration of 500, this output will still be 103. So that is one of the issues. If you, random forest has this issue where, if you don't uh, take the whole range of your data, don't train the model on the whole range of the data, it will basically not be able to extrapolate. It will not be able to go outside the range of the training data that you have. So this is one of the issues with random forest. And the last method is gradient boosting method. So it's essentially efficient implementation of gradient boosted decision tree, similar to random forest, but the internal workings are a little different. The prediction, so basically the prediction, here we took an average of all the outputs. Here we are going to take a sum of the previous prediction and the output from the new tree. There is also a regularization term in the objective function. Not going into math, but it helps basically control the model complexity and helps prevent overfitting. And as I said, final output is the output of sum of the predictions of all the trees. This is a code for it. Again, similar to what we had in random forest. We are going to search through a lot through the parameter space. We are going to search it through the grid CV function that we have, and we are going to search through all of them. This will help us identify which, in that parameter space, what is the best model that we have, using the best estimator. And again, we are going to calculate the R square value for the output. So here you see we get an R square value of 0.96, which is very good. So it is essentially, these are three trees that we have for the same example. It's still the same thing. Here the value is 6.8, 0.8 is 5.52, and so on. And all the output from all these trees are then summed. So that will basically give you your output. This is the output for the time series that we saw. It does quite good. For example, this point where earlier the sensor was reporting very low value for a very high concentration of ozone has gone up to the 1-on-1 line. Now, and I mean, people can say that this may be overfitting. That may be the case, but in this case, it worked. And just to test whether the data is overfit or any of these models that we have seen are overfitting, we are also checking the R square value on the test data set. So we saw whatever we saw till now was on the training data set. We see that the linear regression is in fact doing better on a test data set as compared to 0.83. We have 0.87. Slight improvement even in quadratic regression. There's very minor dip in the R square value for random forest and XGB. So again, these two models are able to kind of go out of the range, out of their training data set range, and basically able to predict well. Here that is not the case, but still it is quite good results from the XGBoost method that we have. So any questions so far till this point? And I'll move on to the next. Few more slides are there. Okay, I'll move and then we'll take the questions in the last. So what are the results that we have observed here? For the non-parametric methods such as random forest and XGBoost, we have very good performance. It excels in capturing the complex patterns in the training data and performs efficiently on the test data set that we saw. We have the numbers here. However, it is sensitive to changes. Accuracy may drop if the test data range is outside the range of the training data. And again, there are still risks of overfitting. Here we have not seen it, but to do an in-depth analysis, that you may find that some of these models may have overfit. For the parametric methods, linear regression and quadratic regression, we have simpler assumptions, and it's very easy to interpret because we get a coefficient for each of the variables. You can actually say that temperature has so and so dependence on the output of the results that we have. Here it is quite difficult to kind of quantify that. And we have better generalization. It is basically reliant on unseen data for long. So you see that if the data is unseen to the model, it still performs very well. There is no dip in the output. So some of the merits, merits and demerits, it has again strong performance. is able to on both training and test data set due to ensemble learning. So because we have multiple decision trees, they all come together to basically give it the output. The performance is good. It is able to handle the non-linearity quite well, interaction features effectively. However, interpretability, as I said, you cannot interpret, you can't sit and interpret the tree that we have as compared to when we have coefficients for some of this in the linear regression, quadratic regression. It is sensitive to noisy data. So if you saw here, there is this one point which is like very high, which is in the EQMS data. And all of these methods, both the non-parametric methods try to fit that point very well. But that is not the case with linear regression. So that this may be an issue of overfitting. So linear regressions and other quadratic regressions might do a better job predicting this point as compared to non-parametric method. And may not extrapolate well, as I said, may not extrapolate well beyond the training data, making predictions outside the train range challenging. For linear regression, again, simple, interpretable, it provides you clear insights about the feature contribution. It's very efficient to contribute even on large data sets. It's very fast. But however, it assumes that there's a linear relationship between the features and the target, which may not be the case always, which may not be able to capture the complex patterns. And it is sensitive to outliers, which may affect the model performance. Quadratic, on the other hand, will be able to capture the nonlinear relationship, and it provides a more flexible model as compared to linear regression. However, as the number of variables increase, it becomes very complex, and it may be computationally intensive to kind of compute as the number of terms increase. So coming back to the Bengaluru issue, this is like the map. So this 14, there are 14 CAQMS stations across Bengaluru set up by CPCB, and CSTEP has put up 40 sensor nodes in Bengaluru at different locations. They're either strategic, or you normally don't get permissions to put up such sensors everywhere. So based on wherever we are able to put sensors, we are also, if you see, some of the sensors are also placed close to this CAQMS station. The reason being, we also want to check how our sensors are performing. If it is close to a regulatory, we calibrated it in office, but then when you put it on field, you need to also check how they're performing over time. So that's when a few of the sensors are placed close to them. For air quality modeling, for a state or a national, at a national level, 14 points are quite good. You'll be able to tell what is the contribution of Karnataka to Tamil Nadu to Karnataka, and so on. But if you want to do Bengaluru urban district to Bengaluru rural district and so on, that becomes very difficult at such small scale. If I were to do hyperlocal level modeling, let's say at 1 kilometer, which again we saw there were 28 pixels at 25 kilometers. If you reduce it to 1 kilometer here, sorry, it was 28 pixels over at 10 kilometer resolution. If you want to do it at 1 kilometer, it's 2800 pixels, which is a lot of points, and we need to validate a lot of them. We have 40 IoT enabled sensors that we have. This is a network of it, and we'll be putting more as and when we find, get more sensors and other things. Now, since these sensors are calibrated against the reference grade instruments, we can rely them on for research purposes, again, not for regulatory purposes. We can rely them on for the research purposes. I can say that I can validate my model using the CPCB data and augment it with the sensors that we have put up across Bengaluru to basically say that the model is well validated. So yeah, this is my last slide. So we are in the process of running models at this scale. It's computationally expensive, as you can understand. You cannot just run model over this part of Bengaluru, because there are contributions coming from outside. So you need to run a model at 1 kilometer for this range, and let's say a 3 kilometer region for a 300 kilometer region around Bengaluru, and a 10 kilometer or 9 kilometer for, let's say, Karnataka state and a neighboring region, and 27 kilometer over India. So that's a time consuming, computationally expensive process. So we are in the process. Hopefully if I'm here next year, I'll be able to share some results. But yeah, this is something that where you can use machine learning to improve your model validation, which is quite important. And air quality models have been gaining tractions recently. So the idea is that you cannot always, you don't have second earth to experiment on, right? So that's when you use computer models to kind of see that if I take this action, what is going to be what is going to be the reaction of that action that I do. So this is like the presentation that I have. So yeah, you can ask any questions if you have.
Okay, thank you, Nirav. We'll open the floor for questions now. Yeah, Bipin.
Hello, sir.
Yeah.
I'm Deepayan from IIT Kharagpur. So I have a question from that coding part. So yeah. Can you please go?
Which method?
Any
of them? Okay.
Just I need a yeah. Let us say this is a time series data, right? So in the train test state, you have used shuffle
Yes.
and random state.
Yes.
So it gets shuffled.
So again, I agree that it is a time series data, but then the concentration of a particular pollutant. So basically, I'm comparing a reference grade sensor, a reference grade monitor to a sensor concentration. So it will not depend on its previous value, right? Because it is at that instant, the concentration is at that instant, so it would not affect. So here it is, I mean, it's a time series, but you are going to use that data as just numbers, not a time series. So there's no temporal relation in the data as such.
Okay. Thank you. Thank you.
Hi, sir.
Yeah.
My name is Deepak. I'm from IIT Roorkee. So I'm interested in that WARF part which you showed. So I want to know the.
I have not shown a lot about WARF,
Yeah.
but I can answer some questions.
So, I mean, so what resolution are you getting out of the WARF which is going into the CAMX?
Okay.
That's
So
one of the questions.
we normally don't. Just let me just go to the slide. Yeah, so this is, let's say, the slide that we have. The WARF part here is run, for our setup, we have run it at 10 kilometers because then it gives us some flexibility to extrapolate to 25 kilometers or 27 kilometers if you need, and go below. Let's say you want to do a 5-kilometer run. So you don't have to rerun WARF every time. You can just adjust your, I mean, of course there'll be loss of information in both the directions, but I think that is still okay, because a lot of the chemistry part and the other things that you see is handled by CAMX. So it's just the meteorological fields that goes into the CAMX part for it. So I think it works. So for our application, it's 10 kilometers. Yeah.
This is just WARF, not WARF Chem.
No.
Only WARF.
Only WARF.
Okay.
Only the WARF part, which gives us the meteorological fields. That meteorological fields then goes into CAMX to do all the chemistry.
One more thing, so the rainfall output from WARF is going as an input for the CAMX model, right?
It does go. And so CAMX, while it is giving you the concentration, it also gives you the deposition of the different pollutants. That deposition comes from rainfall. So that is, again, we don't normally, I mean, we have not analyzed those results, and it's a little complicated to understand that. But it does goes into the CAMX part, and that's when the deposition is takes basically understands.
And the second part of my question is from the validation part. So you showcase the map of sensors, like AQI sensors all around India, right?
Yeah.
So that's how you validate your model.
Yes. So we use that data for the CAMX validation.
Okay.
But we do have METAR and SYNOP data and some other data from other sources for validating the WARF, because that is also important.
Yeah.
So we do that.
So my question is that so your AQI output, sorry, the concentration or emission output from the CAMX is for India and then the surrounding regions also, like the northwest.
No. We don't have access to sensors. I mean,
exactly.
This is an Indian network, so there are places outside, but we normally don't have access. We don't know how they're calculated. Normally don't include in the validation part. We are only focused over India. But those regions are necessary because there is
a lot of pollution.
Yeah, there's a lot of pollution coming from that region. It's not like we have a closed door India, right? We have things coming from outside. So that is why those things are included in the in the simulations. Again, even if we are, let's say as I told you about the emissions also, right? We have emissions. There are some emission inventory over India, but we use global for our research, and our focus is to only improve the emission inventory over India. The things that are coming from outside, we don't know the local realities there, so we'll not be able to improve on them. We kind of work with different partners. We try to understand that, the numbers given by, let's say, domestic sector from SEDS emission inventory, are they correct? If they are off, how off they are, and then we try to fix those. So that is what we do.
Thank you.
Thank you. I think there was a comment from the
Yeah.
online participants.
Uh, uh, Dr. Orpita, maybe you can read out the comment for everyone's benefit.
Let's see.
Sorry,
Okay.
Adway is saying something.
Dr. Orpita, maybe you can read out the comment for everyone's benefit.
Yes, sure.
Just
Nirav?
yeah. Is it full?
Yes. So it says, hi, Dr. Nirav. Thank you for the very nice presentation on machine learning and low-cost sensors to validate air quality models in India. Given the limited number of CPCB monitoring stations in Indian cities and the increasing pollution challenges, how practical is it to use machine learning calibrated low-cost sensors to improve work CAMEX model accuracy, especially for local scale planning and policy decisions?
So thank you, Paparao, for that question. So I think we are going to we have seen that case for Bengaluru where we have implemented sensors at low cost at a local scale, and then there are some state governments who have also done that for their cities. So using that data, if we were to kind of take any actions using or for that matter the management plan, if you want to create such sensors can help. They may be off. So they may be off by a certain amount. Let's say the sensor, the temperature is 28 and it's reporting 27 or 29. That is not accurate, but it is still some information as compared to having no information. So sometimes that also helps. We can downweight such things if we know if some of the sensors are kind of faulty. We can downweight their what you can say that say in the model validation, but it's instead of losing the whole data, it's better to downweight in such case. So I think it is quite possible if we have for local scale modeling, if we have such networks along with the regulatory monitors that we have, it will help us validate the model better. Yeah. There's one more.
One more comment. Thank you very much for the informative presentation. I have one question. If both linear and nonlinear models perform well on a data set, for instance, a linear regression gives an R-square of 0.83, nonlinear gives 0.9, what does this suggest about the nature of the data? Can we infer that the data has a predominantly linear structure with some minor nonlinear patterns? Can linear regression still perform well on data that contains some degree of nonlinearity?
Yeah. It's Harisha, right? Yeah, thank you, Harisha, for that question. I agree, and I think I talked about the fact that these non-parametric methods may be overfitting. And again, I have restricted myself to R square as one of the metric for this presentation, but we do have a lot of other metrics. I think we have a suite of around 10 metrics that we use to kind of determine whether or not a particular model is fit for any application. And I agree that the data is mostly linear. For example, ozone or for that matter PM 2.5, which is linear has a linear relationship with the other parameters. I think linear regression can work well. I believe in the philosophy of Occam's razor. You use the simplest model which is able to explain something like they're similar. So I would go for a quadratic or a linear regression in this because it gives me more leeway in terms of determining what is a coefficient of a particular variable and play around with it. But the idea here was to present all the different methods that we are using at C-STEP, and there are many more methods. So for example, I didn't talk about support vector regression here, but we do have other methods that we use for such applications to calibrate the sensors. Yeah.
Yes, thank you. Any questions from anybody else in the audience, live audience?
Dr. Nirav, this is Adway. So
Yeah.
first of all, my apologies for failing to be here in person. I was supposed to be, but due to some emergency, I had to rush back. I will be back again, and if possible, I will visit CSTEP also once.
Sure. Yeah.
So I had a couple of questions. One is, so you have like used these, or you're mentioning the setting up a sensor network of these low cost sensors. But I was wondering, another would remote sensing or satellite imagery be another source which you can consider, like with like much bigger coverage? Because there is also a lot of work going on where from satellite imagery is used as some kind of proxy to estimate different these concentrations of air pollutants.
Yeah.
Do you have any comment about
Dr. Mitra. So I think I completely agree.
This is not very clearly.
Yeah, so he's asking about while setting up a low-cost sensor network is a good idea, but can't we use satellite imagery, satellite data for this application also? I think I got the question right, Dr. Mitra?
Yes, yes, yes.
Okay. So we do have some satellite products available at very high resolution, about 1 kilometer by 1 kilometer. Professor Sagnik from IIT Delhi has one of the products, and they correlate very well with our models and even the CPCB network. But the problem, it's not a problem, but it's just an observation that satellite again is a top down. You look at the country from the top, and then you have a lot of clouds and other things interfering. So that is when where they use machine learning and CPCB observation data itself to kind of fill that gap. So comparing, something that is created using CPCB data against CPCB data, it is going to give good correlation. But doing it at a hyperlocal level, 1 kilometer or sub 1 kilometer, I think it's good to have a network. We can use satellite as an additional layer of information, but I'm not sure if depending completely on satellite will be
Right,
like
right. Yeah, I agree. I mean, a multimodal approach is most likely the best. The second part of my question was, so like initially you mentioned these emission inventories, right? So like if for the Indian region, do we have updated inventories?
Yeah, so I think the one that we have access to is Professor Chandra's 2015 smog emission inventory. We still don't have, I think 2019 emission inventory is not in the public domain yet. And we have nothing after that. So again, the latest emission inventory that we have is from 2019. The global emission inventory, again, they also take some time. There's a lag time of around 2 to 3 years. So we recently got Edgar 8.1 emission inventory, which is again at 10 kilometers for 2022. So I mean, we do have, but at Indian level, we do have a smog emission inventory, and then there will be very local emission inventory for, let's say, a particular city or a particular state, or someone would have done some research in only one sector. Let's say agriculture waste burning for Punjab. That would be the extent of the information. We don't have an extensive emission inventory for all the sectors, all the possible sectors that we normally have, that we normally need for running such models. So such information is still not widely available. I mean, this calls for this also calls for an effort for all the scientists like academia and even non-profits like us to kind of build a national emissions inventory together. Like US has one of them, which they update every 2 to 3 years. So something like that, an effort to kind of create such an emission inventory is a need of the hour for such models to perform very well. Yeah.
Okay, thanks a lot. So, so actually, one of my PhD students was briefly working on on this matter. I mean, she's right now she's actually looking into estimating some PM 2.5 from satellite imagery. But I think maybe I will write to you sometime later, and I will try to introduce you to her, and then maybe we can have a discussion one day. And
Sure,
about this.
yeah.
Okay, thanks a lot. Thanks a lot.
Cool.
Dr.
So we
Mitra.
can see some collaboration spawning from the
Yes.
presentations, which is great. Any other questions? All right. If
Yeah.
not, then
Thank you.
let's thank the speaker, Dr. Lekinwala.
Thank you, everyone.